You're browsing the website. You found a very interesting link you want to share to your friend. You copy the link. Then you figure it's too long to share in email or message. Then you go to one of the most popular URL shortening service, bit.ly. You paste the link. You click shorten. You get a shortened URL. You copy the shortened URL. You share this URL with your friend. When your friend clicked on the shortened URL, it will actually be redirected to the original link you want to share with your friend. That summarizes our functional requirements. Given a long URL, we should return a unique shortened URL. When user clicks on that shortened URL, user should be redirected to the original long URL. When you create a URL shortening service, the length of the shortened URL actually matters. The shortened URL from bit.ly looks like this. It contains two parts. The first part is the domain, which is customizable per brand, but the length is going to be fixed. The second part is the actual ID of the shortened URL. It contains 7 characters. Each character is either a number, a lowercase alphabet, or an uppercase alphabet. That adds up to 62 different possibilities for each of the 7 characters in the ID. That represents 62 to the power of 7 different unique IDs. Let's assume bit.ly generates 600 million URLs monthly, which is quite reasonable. With a total of 62 to the power of 7 unique IDs, it will take about 489 years to use up all the IDs. Well, if you decided to use 6 characters, it will take about 8 years, which is probably not a good idea. Functional requirements tells us what the system will do. For example, when the user provides the long URL, the system should return a shortened URL. But this is not sufficient to define the behavior of the system. What if the system returns a shortened URL but like in 10 minutes? And also, what if the system can return shortened URL in under 100 milliseconds, but it can only handle 1 request per second? So that's where the non-functional requirements kicks in. Non-functional requirements specifies how the system should perform a specific behavior. In our previous example, we can add a non-functional requirements with specifying the P90 latency to be 100 milliseconds. It defines for 90% of the requests, we should return a shortened URL in under 100 milliseconds, which is quite reasonable. In 2014, bit.ly shortens 600 million links a month, and that those links are clicked on 8 billion times. We'll use those numbers as a scale we should be handling while designing our system. That summarizes our non-functional requirements. With 250 URL shortening requests per second and 3,000 clicks on the shortened URLs per second, we should deliver in under 100 milliseconds for 90% of the requests. Okay, let's talk about the design. Usually the way I would approach this is to start small and simple. We can start with a design that doesn't scale at all. That's totally okay. Then we'll scale up each of the components based on the requirements. In our case, we can start with a very classic client-server architecture. The first thing we want to establish is the API of our service, which defines the contract between client and server. Let's take a look at our requirements another time. With users submitting the long URL, we should return a shortened URL. When user clicks on the shortened URL, we should redirect the user to the original long URL. That being said, we need 2 APIs. The first is create short URL. It's a post request with user provided long URL in the request body. In case of success, we should return 200 status code with shortened URL in the response body. In case of error, we should return 400 if it's a bad request. For example, the client didn't provide the long URL in the request body, or the long URL provided in the request body exceeds a certain length. In case of unexpected error, we should return 500, the internal server error. The second is /ID. it's a GET request. In case of success, we should return 302 status code indicating the browser should redirect the URL specified in response location header. In case of error, we should return 404 when the short URL not found, and 500 in case of unexpected error. API design is one of the most important parts in system design, as it established a contract between client and server. If you want to change the contract later, you may want it to be backward compatible, as you don't want to break the existing client. Usually we want to spend the right amount of time here, have the contract carefully designed. Okay, now let's dive into the implementation. Obviously, we need a persistent layer to start the mapping between the short URL ID and the long URL. Let's start with MySQL. The database table is going to be simple. It's basically a mapping from short URL ID to the long URL with adding a timestamp for creation time. Here is a simplified version of the core business logic we want to implement. Create shortened URL, take a long URL as input. It will generate a short URL ID randomly. We first check in the database to see whether it's already used. If the ID is not used, we'll create a new entry in the database table and return the shortened URL. If it's already being used, we continue the while loop and generate a new one until we find one ID that is not being used. GetLongURL takes the short URL ID as input. It will simply do a query to get the entry with ID equals to the short URL ID and return the long URL associated with that entry. It's pretty straightforward, right? But you'll see the code will get very complicated over time when we start to scale up. There's no way we can handle 3,000 transactions per second with one single server, so we need to scale up. First of all, let's generalize each component we drew previously. Instead of application server, we call it application layer. Instead of MySQL, we call it persistent layer. As we discussed previously, we'll scale up each of those layers to meet the non-functional requirements. Let's start with application layer. Scaling up application layer is usually straightforward. We can add more servers and add a load balancer up front. All the requests will be dispatched by the load balancer to each of the application server. The most common setup for load balancer is round robin. Each request is forwarded to each of the application server in turn. In this case, suppose the TPS is n and the number of application servers is m. The TPS on each server will be n divided by m. The code that we wrote previously will not be working properly in some scenarios. Let's assume we have app server 1 and app server 2. Both receive requests to create short URL at almost the same time. And also the short URL ID that is generated randomly for both servers are the same. When the code runs into this line, as it's not inserted previously, both will return none. Then both app servers will try to insert the entry in the database. One of them will succeed, and the other will fail as the transaction for MySQL is atomic. In the failure case, we'll return 500 as its internal server error. To fix this, we can simply catch the exception and retry. Whichever server failed, we'll retry with a new short URL ID until success. As you may already noticed, even though we have scaled up the application layer, the TPS to persistent layer is still n. We need a way to scale up persistent layer. Let's stick with MySQL database for now and see how can we scale up. We'll explore other options later. To scale up the read requests, we can leverage MySQL cluster with source replica architecture, with one database server as source and multiple database servers as replicas of the source database. All the write requests that go to the source database will then be replicated across all replicas asynchronously. Thus, while reading, we can do a client-side load balancing to choose one among all the database servers. For the write requests, it has to go to the source database server. That being said, we need to change MySQL client so that all read requests will be dispatched to one of the database servers in the cluster. Assume we have P replicas, then the read requests will be evenly distributed among P plus 1 database servers. If we take a look at our previous implementation of getLongURL, now we need to change our code on application server to do the client-side load balancing, to distribute the read requests in a round-robin fashion. The same applies for create short URL. For write request in create short URL, we need to select the source server from the configuration as well. The limitation of MySQL source replica architecture is there's one single source server that handles all write requests. Replica servers only handle read requests. That being said, as write requests to the cluster increase, it reached a point where one single database server cannot handle. How can we scale up write requests? One simple thought is to distribute write requests to multiple MySQL clusters. Let's first take a look at the database transaction pattern for our URL shortening service. There are write requests for creating shortened URLs with inserting short URL ID and the long URL, and read requests to query database with short URL ID. We can actually distribute write requests to different clusters based on ID, as long as read requests with the same ID will be distributed to the same cluster. For example, all read-write requests with ID that starts with A goes to cluster 1, and all read-write requests with IDs that starts with B goes to cluster 2. The technique to split up database across multiple database clusters to improve the scalability of the application is called sharding. In sharding, one's data is broken into two or more smaller chunks called logical shards. The logical shards are then distributed across separate database nodes, referred as physical shards. The example we showed previously is key-based sharding. For each of those read-write requests, we take ID as partition key. To decide which database cluster the request will go to, we apply a hash function to the ID. In this specific example, we take the first alphabet. If it equals to A, it goes to cluster 1. If it equals to B, it goes to cluster 2. Let's run the transactions manually and see how it works. This is our first write transaction. It writes a short URL ID and long URL into the database. By applying the sharding with ID as partition key, we apply the hash function on ID, where we take the first alphabet, which is B. By looking at the sharding configuration, for B, we should write to cluster 2. So the transaction will be written to cluster 2. The same applies for read requests. For the same ID, the hash function always returns the same result, in which case all read-write requests with the same ID will be redirected to the same cluster. Let's make it more general for sharding process. First, we need to decide on what we should use for partition key. We should usually make this decision based on the transaction pattern. Then we apply a hash function to the partition key to distribute the transactions to different clusters. One important note here is that we need to choose the right partition key and hash function so that the read and write requests will be evenly distributed to different clusters. Now let's go back to our URL shortening service and see how we can design our hash function. One way of doing it is like what we did previously. We take the first alphabet of the partition key. Based on its value, we can distribute the transaction to a cluster. For example, if we decide to scale up with 2 clusters, then if the value is in the range of 0 to U, it goes to cluster 1. If the value is in the range of V to Z, then it goes to cluster 2. This hash function looks straightforward, but it does have some side effects. For example, as 62 cannot be divided by 3, 4, 5, 6, 7, 8, 9, etc. evenly, if you decide to go with those number of clusters, one of the clusters is going to handle less or more traffic based on your partition. Let's take another method. If you notice a pattern of the short URL ID, it contains 7 characters. Each character can be either a number, a lowercase alphabet, an uppercase alphabet. with a total of 62 different characters. This is actually a base 62 representation of a number, so we can use a hash function to transform the base 62 number to base 10, then modular by the number of clusters. You'll get a more granular way of distributing the traffic evenly. As short URI ID is generated randomly, it will be distributed evenly this way. Then in our application layer, we need to add actual logic for sharding in MySQL client. Based on the short URI ID of the transaction and the configuration, we should distribute the transaction to the right cluster. But where do we store this information? We don't want to hardcode this information as the configuration can change from time to time. We don't want to store this on a single server as it will be single point of failure. Zookeeper is usually the choice here. Zookeeper is a high-performance coordination service for distributed applications. It's highly available and scalable. It's perfect for our use case. If we take a look at our previous implementation of the getLongURL, now we need to first get the configuration from Zookeeper. Then, when selecting the database, we need to pass short URI ID in, so that based on this value, we can first choose the right cluster with sharding, then choose the right MySQL database with client-side load balancing. The change in create short URL is going to be very similar. Okay, that's it. Now we have our scalable URL shortening service with MySQL. But if you take a deeper look, the design is complicated. MySQL client has to handle all the heavy lifting work, sharding, client-side load balancing, and with introducing Zookeeper to store the configuration of sharding and MySQL cluster, it makes the implementation even harder. But if you think about it, why the heavy lifting work has to be handled by the client? Is it possible for the database itself to handle it? Literally, the database can just wrap everything from what we implemented in client-side into server-side, and expose a very simple interface without client knowing the implementation details.